So it turns out that one of the easiest and most recognizable applications of derivatives is actually with position, velocity, and acceleration functions. Now, those of you who are taking physics or have taken physics may have an easier time understanding these things, but I would caution you, you can't just use your equations of motion to solve all the problems that we have. Those only work for constant acceleration, and so you're going to see a lot of your understanding on these things change a little bit and sort of become more awesome. But before I go any further, I need to make sure we're all on the same page here. I need to make sure we all understand what position, velocity, and acceleration are, and what those functions would be. So that's what we're going to go into next. So the position of an object is basically just the location of that object. Generally speaking, if it's positive, it means the object is above something, or to the right of something, or beyond something. And if it's negative, it means it's below it, or it's to the left of it, it's behind it. Right? So if you've got something and somebody says, let's say P of 5 equals 17, generally speaking, this means that at time 5, the position of the object is 17. So the object is, 17 feet beyond something, or 17 feet above something, or, whatever units you're using. If we were to say that P of 7 was negative 3, well, okay, that just means that at time 7, the position had changed to being negative 3. Okay? It's just showing us the location of an object. So next we have velocity. And velocity is basically the signed speed of an object. And what I mean by signed is that, in general, if you have speeds are always positive. But the signed speed means it's speed with a sign on it, positive or negative. Positive generally means that the object is moving up, or it's moving right, or it's moving forward, kind of in a quote positive direction. Whereas negative means the object is moving down or left or backward. Right? So if for instance someone were to tell you that v of 3 was 5, this means that at time 3 the velocity of the object is 5, and it might be like 5 meters per second, let's say. But and this is where I hope things will get exciting. Let's actually think about this. In fact, let's think just about the units. Let's think about meters per second. That means that this 5 is really an expression of distance over time. And I'm going somewhere with this. We've seen fractions before. This distance is effectively a change in position over a change in time. And where have we seen this talk about change in one quantity versus change in another quantity? What I'm effectively saying here is I'm saying that velocity is the rate of change of position. And I hope that makes sense. I hope that I'm able to convince you here of the idea that when we talk about velocity being speed, when we even look at the units as being meters per second or miles per hour or feet per minute, we are seeing and hearing that as velocity being a change in position compared to a change in time. Velocity is the rate of change of position. But that means we can use the word derivative. Right? This means that the velocity function is the derivative of the position function with respect to time. So if you have a position function, you can find the velocity function just by taking the derivative of that position function. So we need to move on and talk about acceleration now, and don't be surprised if more of this same derivative business shows up. Let's see what happens. So for those of you that are unfamiliar with physics, what is acceleration? Well, acceleration is basically a measure of how quickly velocity is changing. Right? But we know it's coming. More accurately, that means acceleration is the rate of change of velocity with respect to time. So what does that mean in terms of derivatives? Right? It means that acceleration is the derivative of velocity. Now, in the previous slides, I sort of went through and said, when position is positive or negative, this is what it means. And when velocity is positive or negative, this is what it means. With acceleration, that's a little bit more complicated, and I want to get into that now. So what I need to say here is that positive acceleration does not mean the object is speeding up necessarily. It doesn't mean the object's speed is increasing. What it means is that the object's velocity is becoming more positive. Because acceleration is the rate of change of velocity. So if acceleration is positive, it means velocity is becoming more and more and more positive. But that doesn't always mean the object's speed is increasing, and I'll cover that more in the next slide. Similarly, negative acceleration doesn't necessarily mean deceleration, it just means the velocity is becoming more negative. That may be confusing, but I'm going to try and clear it up right here with an example. The example we're about to do is sort of an oversimplification of things. You're generally never going to be asked to do a problem like this, but I feel like going through this example will give us a chance to sort of see some relationships come up. So here we go. So I want to consider an object that's moving along the x-axis. It has an initial position of 9 units, an initial velocity of -4 units per second. Now I want us to suppose that that object has a constant acceleration of 1 unit per second squared. And if you're worried about that unit, don't worry about it. We'll talk about it later. I want to make a chart of the motion of the object over the next 10 seconds. And we're going to use this chart to sort of determine when the object is at rest, so when it stops, and when the object is speeding up or slowing down. So to make this chart, I'm going to need sort of multiple headings. I'm going to need to look at time. I'm going to need to look at position. I'll need to look at velocity, and I'll need to look at acceleration. So we know that at time 0, the position of the object is 9 units, the velocity is -4, and my acceleration is 1. Right? And we sort of want to fill this table out over the next 10 seconds. So now we have to sort of imagine what happens, right? What will have happened 1 second later? Right? And again, this is an oversimplification. This is not perfect, but I'm using it to get us somewhere, right? So up here, my velocity was -4. That means my position was changing by -4 units per second. So 1 second's just gone by. My position is now, -4, 4 less than that, so my position is now 5. Now similarly, my velocity will have changed. If my acceleration was 1, it means my velocity changes by 1. My velocity is now -3. And my acceleration was constant. My acceleration is still 1. Right? So now what about at time 2? Right? At time 2, again, my position will have changed. It will have changed by -3. And again, this is an oversimplification. This isn't strictly speaking correct, but I'm getting us to look at something, right? So my position is now 2, that's 3 less. My velocity also changes. Because my acceleration is 1, my velocity will change to being -2, and the acceleration will still be 1, won't change actually. If you think you've got the hang of that, see if you can fill out the next 2 or 3 rows on your own, and then check in with me, and we'll make sure that we're doing it right. So at time 3, the position will have moved to 0. My velocity will have moved to -1. My acceleration will still be 1. At time 4, my position is, let's see, your velocity is still -1, so this will go to -1. Velocity will be 0, and acceleration will still be 1. Time 5, my position will actually be -1 again, because at this point my velocity is 0. My position is not changing, right? My velocity, however, will have changed. This will now be up to 1. Acceleration will still be 1. At time 6, so now my position was -1. It changes by +1, so my position is 0. Velocity moves up to 2, and acceleration is 1. At time 7, this is 2, this is 3, this is 1. At time 8, this will be 5, and 4, and 1. And I know I said go up to time 10, but I think this is probably enough. Maybe I can fit one more down here at the very bottom. I could say at time 9, my velocity would be up to 9, my velocity would be up to 5, and my acceleration would still be 1. So I've got this table of stuff, and we may be looking at this going like, okay, what's the point? What does this matter at all? I want to be able to answer some questions, and I'm hoping we'll be able to do that. And we can even see the questions up above. The questions were, when is the object at rest, and when is it speeding up or slowing down? So when is the object at rest, and when is it speeding up or slowing down? So let's handle that rest first, and we even sort of briefly mentioned that. Where does the object stop? And when does it happen that the object's position is not moving? Right? That happens right in this region. And what was it that caused that? We find that an object is at rest whenever its velocity is 0. So that's the first conclusion that I wanted to make. We can see here that an object is at rest whenever its velocity is 0. So if you're ever asked to find when an object is at rest, or when it's not moving, you set the velocity equal to 0. It has nothing to do with the acceleration, it's all about the velocity being 0. Now my second question from above is, when is the object speeding up or slowing down? right? And so for this one, like, I want you to look at it and sort of think about it. Like, look especially at your velocity column. Look here at these velocities. When is the object speeding up? Well, the object is speeding up down here, right? My velocity went from 1 to 2 to 3 to 4 to 5. That's us speeding up, right? When is the object slowing down? Well, up here, my velocity was going from -4 to -3 to -2 to -1. I mean, I started out with a velocity of 4. That's pretty quick, right? Then it was only 3. Then it was only 2. Then it was only 1. Then I stopped. And then I started speeding up on this end of things. So how can we tell when an object is speeding up or slowing down? It turns out that it comes from the relationship between velocity and acceleration. If velocity and acceleration have different signs, if this one is negative and this one is positive, then they're fighting against each other, right? The velocity is saying, I'm negative, and the acceleration is saying, yay, become more positive then, right? If your velocity is negative and you're being asked to become more positive, you're going to be slowing down, right? Contrast that with down here. Down here, velocity is positive and acceleration is also positive. That means they're working together. Velocity is saying, hey, I'm 2, and acceleration is saying, yay, let's +1, now your velocity is 3. Then the velocity says, I'm 3. When we add 1, we're up to 4 now. If velocity and acceleration have the same sign, both positive or both negative, then the object is speeding up. And if the velocity and acceleration have different signs, it means they're fighting against one another. If one is positive and one's negative, it means the object is slowing down. And so I'll write that conclusion down below. I know this has been a long video. Thanks for hanging in there. If you have questions about these things, if something's not making sense, I cannot say enough times, write it down and be ready to ask about that. I'm going to go into an example in the next video, and I hope in that example to sort of make things a bit more concrete. So I'll see you there.